Good morning, everyone. This is an introduction to the third target that we are doing. So we've spent quite a bit of time working on plots that look like this right here. And specifically what we've been thinking about is what equation would give us a plot that has that shape. What does it mean that the plot, is hits at that spot right there? That's the y-intercept, right? And then what we've really been paying attention to is how things grow. So for example, if I let this thing grow horizontally this far, it grows vertically this far. And comparing the size of that growth with the size of that growth. Now, everything we've done so far has nice and constant growth like patterns, right? This growth between horizontal and vertical is the same. So we do call this the slope. So you've all seen that. And it's just a comparison between how things grow up and down and how things grow left and right. This is, I'm hoping that you guys are all in a place where this sort of makes sense. A comparison between how things are growing up and down versus left and right. So for example, if we did, volume of a liquid versus the mass of a liquid, we could see as you grow the volume of liquid that you have, here's how much the mass grows. As you grow the amount of volume of liquid that you have, here's how much the mass grows. If I add 1 milliliter to my liquid, how many milliliters of mass will I end up getting? And different liquids will be different. That is what the slope means there. All right, so target 3 is similar, but it's a little different. See, plots don't always look like this. Sometimes plots look like this. Or sometimes plots look like this. Or sometimes plots look like this. There's a lot of different shapes that our plots can possibly take. And while I don't think we're in a place where we can describe them with an equation yet, I think we can describe them in words. So that's our goal. Is target 3 is, can you describe how things are changing in a plot that is not a straight line? I do not need you to do this mathematically. You will not be writing out equations for this. You'll just be telling me in words how the growth is changing. So let's go ahead and look at an example. If you've ever seen a clock like this, you ever seen one of these guys? This part right here is called a, this is right here is called a pendulum. And the pendulum is actually what this type of clock uses to keep time. There's kind of an interesting thing where if you have a pendulum, and as long as you don't mess with the pendulum, it will always rock back and forth in the same amount of time. So let's go ahead and take a look at this. So if I have some pendulum, oh, not that one. If I have, there we go. So if I have some pendulum, the length of that pendulum actually controls the amount of time it takes for the pendulum to go back and forth. So whoever made this clock made the pendulum right here a very specific length so that when the pendulum goes back and forth, that it controls how quickly the hands of the clock move. Anyhow, you don't need to explain clocks to me. In fact, I'm not going to probably ever ask you about pendulums again. But I am going to have you look at this plot real fast. So here is a plot. Here's how long the pendulum is, like physically. What is the length of the pendulum? So that would be like if you put a ruler on here, how long is the pendulum? And then here, the period is the amount of time it takes for the pendulum to go back and forth and back and forth and back and forth. So if you have a pendulum that's this long, what is that, like 17 centimeters or 16 centimeters or something? Actually, more like 13. Well, it takes about, I don't know, 0.7 seconds to go back and forth. Here's a good one. This thing is probably 55 centimeters long. Well, it then takes 1.5 seconds to go back and forth. If you wanted a pendulum that takes exactly 1 second to go back and forth, we would expect it to hit right about here, about 22, or sorry, that looks like more like 25 centimeters. So different amounts of different lengths of pendulums take a different amount of time to go back and forth. Again, I'm not going to expect you to do this mathematically, although if you want to know what the equation would look like, it would look like that. Yeah, we're not doing that. We're not in a place where we can do that. But we are in a place where we can think about the growth. So here's the sort of question I would ask you. Looking at this graph, how are the length and the period related? And how does this change as we change the length? So basically, I'm going to ask you for an interpretation of the shape of this graph. So if I said, hey, describe the relationship between the length of a pendulum and the period of the pendulum, you could pretty easily say a longer pendulum will have a longer period. And you can see that here. Ooh, excuse me. And you can see that here because here we're going to make the pendulum longer. We make the pendulum, let's pick a color you guys can actually read. We make the pendulum longer, and what that happens is the period gets bigger. Longer pendulum, bigger period. Longer pendulum, bigger period. Longer pendulum, bigger period. Longer pendulum, bigger period. Whenever we make the pendulum longer, the period gets longer. That's nothing new and different. But there is something that's different. So here, just to kind of give you a comparison, I'm going to say, well, what happens down here if I make this, I'm going to say that's about 10 centimeters longer. If I make this thing, let's make that prettier, 10 centimeters. If I make my pendulum 10 centimeters longer, it seems to go from about 0.7 to about 1.0. That's a total of a 1.3 second gain. Making my pendulum 10 centimeters longer seems to raise the period by 1.3 seconds. That's nothing new. We have done those comparisons for months now. But let's look over here. I'm going to go another 10 centimeters or so. And we're no longer going up by 1.3 seconds. Now we're going up from about 1.7 to about 1.8. This is only about a 0.1 second growth. Oh, sorry, this is a mistake. It's not 1.3, it's 0.3. So here, 10 centimeters gets us 0.3 seconds. Here, 10 centimeters only gets us 0.1 second. As we grow the length of the pendulum, we are getting a longer period, but we are getting less and less growth in the period as we make the pendulum longer. A longer pendulum is affected less by added length than a shorter pendulum is. A good way to see this is with slopes. So, let's pick again a color that you guys can actually see. How about hot pink? That'll work. So if we go ahead and look at the slope of this line, you can see how the slope is changing the whole time. Here we have a steep slope. That means we get a lot of period for the length. Here we have a really shallower slope. That means we get less period for the length. So if I said to you, describe how this relationship changes as we make a longer pendulum, you would say a longer pendulum, oops, if I can spell correctly, a longer pendulum changes its period less when lengthened than a shorter pendulum. Now, let me describe how I got that sentence, right? I think I've kind of gone through it a little bit, but I just want to make sure that you guys are understanding. So one more time. When we are describing slopes, when we are interpreting slopes, we can always describe a slope with a for every statement. For every 10 centimeters of length, the period grows 0.3 seconds. That's what this slope right here would mean. But let's compare that to here. For every 10 centimeters of length, the period grows 0.1 seconds. The 10 centimeters of length does more when we have a short pendulum than it does when we have a long pendulum. Those are the sorts of relationships I'm going to want you to find. Notice I didn't really do any math here. I don't even really necessarily need numbers in your answer for this, but I do need you to tell me about the growth rates. I do need you to tell me about how things are changing as we go through this plot. Now, it's not always going to look like this. Like I said, there will be other shapes. Here's the one from our pendulum, right? As we make the pendulum longer, we get a large change in period, but as we make the pendulum longer here, we don't get a larger change in period. So this sort of matches the shape of our pendulum, but this doesn't. Let's turn that off, Helen. This doesn't. This is a different shape. Here, a change here gives a big change in the y-axis, but that same little growth here gives a tiny change in the y-axis. Look at this one. At first, this change gives, this one change in the x-axis gives a small change in the y-axis. But over here, that same change in the x-axis gives a large change in the y-axis. I should be able to give you about any shape of graph. I will probably limit it to some simple shapes like the ones you've seen here. And in these simple shapes, I will expect you to describe to me the relationship between whatever's on your x-axis and whatever's on your y-axis, and then to describe how that relationship is changing. You will not have to use equations. You will not have to use numbers. We are not at a point where you can do that mathematically except for the linear stuff. Go take some Algebra 2 and whatnot, and you'll be able to do these. These are possible. They're just a little beyond where we're at. All right, everyone, we'll call that good. Please do let me know if you have any questions on this. I'm hoping you've had a chance to watch this video. I'll probably post the first assignment for this on Monday. Have a nice day.